Okay, now we are discussing about Hall effect. So, what is mean by Hall effect? So, simply this can be defined as when an electric current is passed through a conductor along the x direction and a magnetic field is applied along the z direction, then an electric field will develop in the conductor along the y direction. This phenomenon is known as Hall effect. The electric field the electric field thus developed is known as Hall field. We will explain it how it works. So its physical explanation goes like this. So here I have shown in the figure. I will take this picture. So the electric field is applied along this direction, x direction, along this x direction, and the magnetic field along the z direction. So this is the applied field direction. So a current will flow along this direction. So we are considering a metal rod like this, so a rectangular rod like this. So we are applying an electric field across this metal rod. So the current will flow uh, from this end to this end, so this along this direction. So the electric field is along this direction. I have shown this here. So the applied electric field will be along this direction, along the x direction, and the current density is along this direction. Okay, so this is the direction of magnetic field. And now what will happen? So as the field direction is along this direction, the electrons will be moving in this direction, because the current is flowing in this direction, means electrons are moving in this direction, that is in the minus x direction. This is x direction, so this is minus x direction. So electrons are moving in the minus x direction. Now the magnetic Lorentz force, the total Lorentz force experienced by the system will be that due to electric field and magnetic field. So I am talking about the magnetic Lorentz force experienced by this electron. So the magnetic Lorentz force can be expressed as F is equal to Q into V cross B, where V is the velocity of the electrons and B is the magnetic field. So what will be the direction? We can check the direction of this magnetic Lorentz force. So Q is minus E here, because the moving particle here are electrons, and B cross B. So the direction of velocity of electrons is in minus x direction. So minus x, and the magnetic field is along z direction. So this minus and this minus will become positive, and x cross z will become minus y. So the magnetic Lorentz force experienced by the moving electrons in the conductor will be along minus y direction, that is in downward. This is the y direction, so minus y direction is here. So the magnetic Lorentz force will be along minus y direction. So these electrons are experiencing a magnetic Lorentz force in the minus y direction. So the electrons will have a tendency to come downward like this, as they were moving initially along the minus x direction, but due to the magnetic Lorentz force, these electrons are moving downwards the conductor we are considering. So what will happen as time continues? This a large amount of electrons will accumulate on the bottom side, so that a positive charge will be developed on the upper side. Okay, so that means an electric field is developed along the minus y direction. Okay, minus y direction. So due to the magnetic Lorentz force experienced by the electrons, an electric field is developed in the minus y direction. Okay. Now this I will take another note. Minus y direction. So I have shown it is it's in figure. Now what will happen? The force due to this electric field on such electron will be in the positive direction, and this opposes the magnetic Lorentz force. That is, so an electric field is experienced by this, electric field is developed along the minus y direction, and so the force experienced by this electric field will be this is the magnetic Lorentz force, this is the Lorentz force by this electric field, which will be by definition q into E. So q is minus E. Here Ey is the field developed along the minus y direction. So its direction can be found out by putting a minus sign here, because it is along the minus y direction. So its direction will be of in the positive direction. So these electrons experiencing a force force in the plus y direction. So see, here the magnetic Lorentz force in the minus y direction, and the force experienced by this electric field will be along the positive direction. So both these forces are in opposite direction. So the electrons were drifting downwards due to this magnetic force. So this will stop when these two forces balance each other. So when these two forces balances, these electrons will move move towards left with a constant drift velocity. Okay. So as the charge accumulation increases due to the magnetic Lorentz force, the strength of the opposing electric field increases. That means due to the magnetic Lorentz force, electrons will be accumulating at the lower side, and a field will be developed with that field is known as Hall field. That is the field that we have shown here. That is the field in the minus y direction, which is in opposite direction to the opposite direction to the magnetic Lorentz force. So this is the Hall field. When the two forces are balanced, the charge accumulation at the bottom side stops, and the electrons will be moving in the minus x direction with a uniform drift velocity. So this is the Hall effect. This is the physical explanation of Hall effect. Okay, so the condition for steady state flow of electron is the balancing of, or the equilibrium at which the magnetic Lorentz force and the force experienced by the Hall field balance each other. So this is that condition. This is the force experienced by this Hall field developed, and this is the magnetic Lorentz force. When these two are balancing, sorry, the electrons are moving in the minus x direction with a uniform velocity. So this equation can be written like this. From this, Ey is equal to minus Eb tau by m into Ex. The derivation of this equation I have given at the end of this note. You should try it out as a homework. Okay, derivation, you should try it, the derivation of the this equation as homework. Now what is Hall coefficient? Hall coefficient is defined as the ratio of the Hall field to the product of current density and the applied magnetic field. So this is Ey by Jx into B. Jx is equal to, Jx is the current density, it can be defined as sigma into Ex. So substitute the value of Ey here, so we will get this equation like this. So cutting the terms which are cancelling, and we will get RHS is equal to minus 1 by NE, minus 1 by NE. This is Hall coefficient. The unit of the Hall coefficient is given here. In equation 2, in this equation, Jx and B are the applied current density and magnetic field magnetic field. By measuring the Hall field Ey and using equation 2 we can calculate RH. So when we are doing the experiment, we can measure the Hall field developed and we know the value of applied magnetic field and current flow. From these values we can calculate the value of RH, Hall coefficient. So what are the informations derived from this value or coefficient of Hall coefficient? From the value of Hall coefficient we can calculate the carrier concentration in the conductor using equation 3, this equation. So what are the main type of carriers in this conductor that can be derived, that can be concluded from this, from the value of the Hall coefficient, because the sign of the RH gives the nature of the free charge carriers. That means if RH is less than 0 the carriers are sorry, if RH is less than 0 the carriers are electrons. Means a negative sign is already included, considering a negative sign is already included in the equation considering the negative charge of the electrons. So if RH is negative means the carrier concentration, the main charge carriers are electrons. If it is greater than 0 the carriers are holes. Okay, so these are the conclusions uh, derived from the value of Hall coefficient. And the term B into RH is known as Hall resistance, because we know V is equal to IR, so R will be V by I. Talking in that sense, Ey by Jx will be rho h. So from this equation, Ey by Jx is equal to RH into B. So RH into B is known as Hall resistance. Okay. So I have given here a note at the derivation of the equation, which I had told you to try it as homework. So I have given it here at the end of this note. So you should try it as a homework. Okay. So this is all about Hall effect and Hall coefficient.